Okay, thank you. Thank you very much for this opportunity. So I'll be talking about magnet development for future colliders, and very much piggybacks onto what Steve Gorley just talked about, especially with the U.S. Magnet Development Program. So most of this is related to the U.S. MDP. But the outline I wanted to come up with is first start with just a reminder of the magnet needs for future colliders. Talk about the example of enabling magnet technology to kind of situate ourselves, and that's in particular the luminosity upgrade of CERN. A few words about how I see HEP strategy for large-scale technology development and how that plays into to colliders and especially magnets for colliders. And then I'll dive into the U.S. Magnet Development Program, our recent revised roadmap, and how that is aligned with the strategy of high energy physics and the P5. And then talk about a couple of major recent accomplishments. I won't delve into all of the stuff we're doing within the program. Not enough time for that, but I'll show a couple of accomplishments in the last year. Then a few words about synergies and collaborations. So to start with, hadron and muon colliders are really critical, are the primary energy frontier options. And in that realm, the ones that relate to magnets technologies are, of course, the muon collider and the hadron collider, like the FCC-HH collider. So there's a bunch of metrics that tie into the physics or the reach of the collider. Here's one metric is the integrated luminosity per energy input. So that's kind of a sustainability or how efficient is a collider. And so you can kind of see where the HH would land, where a muon collider would land. Tied to that, of course, muon collider versus so lepton versus a hadron collider, you have the physics reach and the energy needs. And so we usually say about a factor of 7, but you can kind of see depending on the physics that might change. And so when you're comparing these, you'd be saying that something that's kind of in this realm on a muon collider is somewhat equivalent to the physics reach of 100 TeV collider, a hadron collider. And so in any case, so we'd be kind of looking at the magnet technologies for variance anywhere from 3 to 10 TeV on a muon collider, or kind of in the ballpark of 100 TeV for a hadron collider to do somewhat comparable physics, let's say. And then the machine just looks very different. Now, in any case, both of these machines are heavily dominated by the magnet technology. So one study, I think this was from the HH side, estimated that the magnets are about 70% of the collider injector cost and about 50% of the overall project cost. So we are kind of the elephant in the room in terms of what is feasible for a future collider. So the onus is on the magnet side to really develop technology that can enable these kind of colliders and to work to bring the cost down to make these potentially feasible. The muon collider has all these elements, the front end, and then the cooling, the acceleration, and the collider ring. All of these have fairly complex magnet needs. In the hadron collider, it's primarily the dipoles for the ring magnets, and of course the interaction region quadrupoles that are the technical challenges. So for a 100 TeV collider, that you can the idea there, what CERN is proposing, of course, is to do like an electron EE collider, and then use that tunnel in the future for a hadron collider, and they would be talking about anywhere from 14 to 20 Tesla magnets. And that is a trade-off in feasibility from the magnet technology and the cost of the system. And now if you look at what that means from superconducting magnet side, all of our colliders to date use Nibium Ti. For the first time in the luminosity upgrade of CERN, we'll be using Nibium 310, where we're seeing fields on the order of 12, 13 Tesla on the quadrupoles that are going into the tunnel in the next couple of years. And then the option for a higher field, ultimately you would have to go beyond Nibium 310 into high temperature superconductors to attain fields that are up above, say, 16, 17 Tesla. So that's really these are the options of superconductors that we have to work with. So this is just a picture of what the FCC would look like. Here's the LHC, and you can see this monstrous tunnel. I think we're all aware of that. The other thing that on any of these colliders, is that the time scales are very long. And it's not just long because the technology takes that long to develop. It's the technology. It has to be developed. It has to be ready for a project, and then the project itself takes a long time because of the scale of the project. So we just have to realize the timescales are long, and we have to start now in order to get to an actual collider in anywhere, even decades away. We have to start now. Okay, so just looking at magnet needs, if we looked at an EE versus an HH machine, so the EE really isn't pushing the magnet technology per se. Doesn't mean there's not a lot of challenges to bring the cost down, et cetera. But it's really not a driving magnet R&D, let's say. What's driving magnet R&D is any potential need for a hadron collider. So hadron collider or a muon collider. Those really need us to develop magnet technology to enable these to be competitive and to be done in a cost-effective manner. So the ring dipoles, we need to get to the field that we need. And there's options there, all HTS, maybe 310, or even a combined hybrid HTS-LTS. There's cost reduction. For ring dipoles, there's thousands, so we would need to industrialize these. And then perhaps even more challenging are the IR magnet quadrupoles. And there again, we have options in terms of the technology potentially. Cost reduction is still an important thing, probably not as important as the ring dipoles, but still the IRs are a costly endeavor. For a muon collider, there's many things, as I mentioned, already from the production side. There's a challenging high field solenoid needs. For acceleration, there's fast ramping dipoles or steady state magnets that are in a fixed field alternating gradient type or fixed field accelerator type solutions. And so we want to explore these kind of options. The cooling, everybody's aware on a muon collider, you need the cooling to bring down the emittance. There we need high field solenoids. Again, it's in a complex environment, changing field orientations, et cetera. And so these are very challenging systems. Then the collider ring itself needs large bore dipoles. There's a large radiation environment, so we need a lot of shielding. And so we need large bore dipoles. And then the detector IR also has its own needs in terms of large bore high field quads. So there's a whole gamut of magnet technologies needed. And what we can do is try to, of course, MDP, I'll show you in a bit, is working to address many of these, not all of them, but combined with synergies with industrial applications, with the high field magnet program at the National High Magnetic Field Lab, and with fusion together, I think we can address the main needs from a magnet development point of view for a muon collider. And Yoon-Ki showed this picture that, in principle, a muon collider could fit on the Fermilab site. Note that, interestingly enough, here the storage ring is the intermediate one. The largest one is one of the fast ramping rings to accelerate the muons. So I just wanted to show this slide. I've showed it before. I like it because it kind of situates, the importance of GARD, the General Accelerator R&D, because that develops a core technology that then can seed directed R&D to enable projects. So when we're talking projects at the scale of a collider, this is a very nice paradigm. It's been very successful, and HEP, I think, has taken the lead on kind of using this very effectively. And so it really balances long range R&D and preparation for projects. So this is the example of that. So in 2003, the LARP was initiated, the LSC Accelerator Research Program, and that really built off of technology that existed in base programs that are developed in 9310 to a degree, and then took that and did kind of a down select, a development combined with a down select, ultimately leading to a design that could be, that enabled the project, AUP in the US and the HiLumi at CERN, to be initiated, let's say. And so you can kind of see this was something like a 13-year development program, or I would say a technology readiness program, that then led to a decade-long actual project to do the luminosity upgrade. And by the way, we're just in the process of completing the last of the magnet assemblies at Berkeley. For that, this will then ultimately go to Fermilab for the final suite of magnet assemblies, cryo module assemblies that then get shipped to CERN. So this project is deep in its coming to fruition. So the GUARD, the MDP. So what we have, this program has been going on now for many years, thanks to HEP, pulling together Fermilab, Berkeley, Brookhaven, and the High Magnetic Field Lab, the Applied Superconductivity Center at the High Magnetic Field Lab, into a national program. So we have a coherency and a structure and a focus to address magnet development for colliders. And so what we've done was we've updated our roadmap to align with the P5 and with HEP's general strategy. So there we are pushing for large bore 9-3 tin magnets. They are highly relevant to the muon collider storage ring. But for us, they also serve as a background field for HTS magnet testing in an accelerator magnet configuration. So that's an option for the colliders and to use hybrid magnets, but it also helps us develop the technology of HTS, high temperature superconductors, potentially for standalone all HTS accelerator magnets. But this is the fastest way for us to develop the technology in the most effective manner. This is an area that's new to us, is that we've incorporated now high field solenoids for HEP. So this leverages significantly the work going on at the High Magnetic Field Lab, but we want to tailor this to the needs of HEP. So that's both for the muon collider, as we saw, a lot of solenoid needs, but also for axion search magnets, for example. The technology we're working on here is highly relevant for axion search. This is always supported by science of magnets, the advanced modeling, diagnostics, et cetera, and materials and conductor characterization, for example. And then we've added a new element down here where we're trying to make sure that we are reaching out to the broader community to make sure that we are addressing the not exactly specific needs of a muon collider or a hadron collider, but that we are communicating to those groups what the limitations are in terms of what's feasible, what's doable. And we can also highlight what elements of the magnet technology are particularly challenging. And maybe there's ways that the collider and the magnet technology can work together to make things more effective. So that's how we've created our updated roadmap for the program. And then we, of course, leverage synergies with Fusion and with the High Magnetic Field Lab. So central themes are things like understanding the disturbance spectrum, what causes magnets to quench and to train, and to develop stress management concepts to enable high field, to avoid degradation. We do that through fast turnaround platforms, subscale magnets, mirror magnets, et cetera. We develop a variety of advanced diagnostics. We develop and demonstrate HTS magnet technologies, high temperature superconductors, mainly REBCO and bismuth 2212. And there it's really developing the technology, developing conductors, developing cable architectures, the magnet fabrication processes, et cetera. And then we want to explore the viability of this hybrid magnet technology, at least for developing HTS, but potentially even as a solution. And then, of course, we want to work with industry to advance superconductors tailored to HEP needs. And so there we have our annual low temperature superconductor workshop, for example, and we have strong university engagement on advancing superconductors. So a few results here. A few years ago, so this is already a bit old now, this is back in 2020 or 2021, we built a magnet that was a traditional cosine theta, 4-layer cosine theta magnet, got to 14.5 Tesla, kind of a record result. It was very timely for the FCC studies at the time. But it was an R&D magnet, and we tortured this magnet. It trained up. This was our first round in blue. We reloaded the magnet because we hadn't provided enough pre-stress, but that was kind of part of the intent, was to learn, increase the pre-stress. It trained more, but it got to the higher field, and then we saw kind of a plateau and ultimately degradation. So the conductor was damaged due to the stress state incurred at the 14.5 Tesla realm. So what we can say is the highest priority issue is degradation. Of course, a collider can't have magnets that degrade. The second priority, of course, is we'd like to not have it start training very early. We'd like to minimize the amount of training quenches we need. And so part of that is having a training quench at a fairly high current. And then the third priority would be the training rate that we'd like to also increase. So where did we go? So we started with incorporating stress management. So there, what we do is we incorporate structures that capture the superconductors along this azimuthal path. Otherwise, the forces build up onto the midplane in traditional magnets, like what's used at CERN. the LHC or the Tevatron. They always had a peak stress on the midplane. And here we capture it. So that's a form of what we call stress management. And we've been pursuing two approaches. One, stress managed CT. It looks like a traditional cosine theta, but is much more efficient in the use of, it is efficient in the use of conductor, and it does a partial stress management. You can see groupings of cables are grouped together, and then that force is captured by a structure here. And then we have the CCT, canted cosine theta, where every cable is captured. So it's kind of the limiting case of maximum stress management. Both of these are being pursued within our program. And so here's some results. So on the CCT, we switched to a subscale, so very small magnets, quick turnaround. We can do these in a couple of months or so. And we've done many of these magnets now. You can see there's two layers and surrounded by an aluminum shell. And this is our traditional thing that we were seeing. We would see training like this. It looks kind of noisy, but it's a traditional training. If you overlap them with like the luminosity, the high lumi quads, you would see not too different a behavior. This one might be a bit noisier, but it's otherwise similar. And it kind of trains up. There was a thermal cycle, but it continued to train up. And along the way, we worked with collaborators at PSI, for example, in Switzerland, and where they were probing different epoxies, and among other things, they tried wax. And it looked very intriguing in their simple experimental test that they were doing. And that sowed the seed for us to try that in the subscale. And lo and behold, we found this fabulous result here, where essentially we got to short sample almost immediately. So that's the limit of the superconductor. We can't expect it to behave better than that. We also did this then where we filled that wax with aluminum oxide to give it a mechanical structure that's a lot more like a traditional epoxy. And we largely retained that excellent performance. This was in a subscale, so we followed that up with a magnet that's at a larger scale, so at a 10 to 11 Tesla scale, called the CCT5W. This again was fairly rapid development, so we were able to do this magnet in about a year. It uses the AUP conductor, the same conductor that's used in the luminosity upgrade, a slightly different cable, but the same conductor. Two layers again, similar kind of structure, but with a 90 millimeter bore, so fairly large bore. And this is the result we got just this last spring. So this was a previous magnet that was otherwise identical, 90 millimeter bore, but with the traditional epoxy, the same epoxy that's used in the luminosity upgrade of CERN, for example, the AUP magnets, had this kind of training behavior. This magnet, so otherwise identical, started training a few thousand amps above, so basically above 90% of the short sample, and fairly quickly at 4 Kelvin went to short sample here, which is the 1 here at short sample. Then we went, this was tested at Fermilab, so they were able to go to 1.9 Kelvin, and there it did continue to train up. So this is training at 1.9 Kelvin here, up to short sample at 1.9 Kelvin. So the important thing here to remember is that here in, for example, the luminosity upgrade of CERN, we're operating our magnets at about 78% of short sample because of the training and the uncertainty in the performance. So that difference there of about 15% is really cost. So for a future collider, this is hugely impactful. So it impacts the collider cost, and since we didn't see any degradation here, we're ready to scale to the 14 to 16 Tesla level, which is our next goal. One other example of recent result is on the high temperature superconductor side. So here we work with both Bismuth 2212 and Repco conductors. In this case, I'm showing a result from Repco. So this is a company makes this ACT, makes this cork cable. We purchased the cork cable from the company, and then we've been developing the magnet technology. Here's a 6-layer dipole, again in this canted cosine theta architecture. We've incorporated fiber optics in every layer of this, et cetera. These are distributed fiber optics, so we can get strain all along the length of the fiber optic, and so all along the cable on every layer of the magnet to help us understand the behavior of the magnet. And in this case, the magnet achieved 6 Tesla, which I believe is a record given the 60 millimeter bore. So this is an excellent result on the US side of using Repco in a accelerator dipole configuration. We've also got some magnetic measurements showing there is, of course, a hysteresis in the transfer function. Not unexpected with these high temperature superconductors, REBCO in particular, which has a large magnetization surface. But so we're starting to understand the behavior of the magnet here. So back to the roadmap, I think what I wanted to point out is that the magnet research here in these areas 1 and 2, are highly relevant to a hadron and muon collider. They also have high relevance to axion search magnets. Axion searches are exploring both dipole and solenoid configurations as well as toroids, but the technology here is very highly relevant. A major focus of our program is on the science of magnets to have lasting impact. And this is important because it has benefits to other projects ongoing, like the EIC, for example, both in terms of the people, the expertise. A lot of the people that worked on AUP also work on within the magnet development program. And now a lot of people are also helping the EIC. And some of the science of magnets here in terms of modeling and diagnostics, et cetera, are being used to help those projects. And then the new roadmap enforces a strong interfacing with collider designs to make sure that the collider designs know the limitations and that we know the needs of the colliders as well as possible. So next major milestone for our program is to get the HTS into a background field in this hybrid magnet configuration. So we have a magnet ready, and we expect to test that within the next couple of months. So strong synergies exist with fusion, REBCO research. So here, for example, there's work going on at the Magnet Lab, coupled with Princeton Lab, and staff from MDP to understand the behavior of quark, for example, in a high background field in a solenoid configuration. So very interesting and useful results already being obtained there. And then I'd like to point out that the Office of High Energy Physics and Fusion Energy Sciences are jointly funding a large bore cable test facility. So this is a massive magnet. So we're building the magnet at Berkeley. The facility is being prepared at Fermilab. The pit is there. The cryostat is there. And so this will be a record magnet. We're promising 15 Tesla and a large bore, primarily designed to help test current high temperature superconductor cables in a background field. I want to just point out that our magnet and conductor plans and roadmaps are well advanced here in the US, but also globally. So we've been well established now. We're fully functioning group, I would say. The Europeans high field magnet program is now established, and it's kind of developing quite rapidly in the last couple of years now. So there's a lot of collaboration between us and the HFM. There's also very nice efforts going on in Japan and the US-Japan. I know it's a small program from high energy physics, but for us it's very, very much appreciated. And it allows us to interface with colleagues from KEK, for example, but as well as universities. And there's also coordination between CERN and KEK, for example. And then China is also doing making very good progress. They're approaching record fields on multiple fronts as well. And I would just like to point out that we have very strong collaboration with industry, with other universities around the world, as well as other labs. So in summary, future colliders depend critically on magnet technology. HEP invests in magnet technology through the U.S. Magnet Development Program in GUARD. We've updated our roadmap a couple of times now, and most recently, just 6 months ago or so, to align with the most recent P5 and with HEP's strategic vision. Recent progress has potential impact on collider performance and cost. So that's not an easy one for us to address cost. But I think some of what we're doing, we're seeing that could have important ramifications for cost for colliders. So we're trying to make things in a way that they could be industrializable and improve the performance of colliders. And we're increasingly focusing on advancing HTS accelerator magnet technology. If there's a real breakthrough in the cost of the HTS materials, we want to be ready to fully leverage that. And I just wanted to point out again that there's strong collaborations exist on the international front, and strong synergies are leveraged with fusion. And so with that, I just want to show the team, the US MVP team at a recent collaboration meeting. Thanks.
Thanks very much, Sorensen. We have several questions. First from Dimitri. How is MDP involved in midterm projects such as EIC and FCCEE?
Yeah, so I think the EIC, certainly I see a lot of ways. So MDP, of course, isn't going to, we're not tailoring any of our work to address EIC per se. What we are doing though is first of all, is staff. MDP has developed a lot of expertise over the years, and we have young folks coming into the MDP, and those people are always are never 100%, very rarely 100% working on MDP. They help on projects all over. So a lot of them have been working on AUP, the Accelerated Upgrade Project, but many of them are now also working on EIC. Certainly at Brookhaven, there's people in MDP that are heavily involved in EIC, and now more and more we can see Fermilab and Berkeley people also engaged in EIC. So I would say it's like staff expertise that is being applied to those projects. But I would say also MDP technology is being applied, especially in things like diagnostics, in modeling capabilities. Of course, when we've developed complex 3D modeling capabilities, the EIC can directly leverage those modeling expertise and capabilities in support of their magnets, and also similarly on diagnostics.
Thank you. We have a question from Heidi. Can you comment more on the connections to fusion R&D?
Yeah, so fusion is almost solely focused on REBCO, rare barium copper oxides, and that's a heavy part of our HTS portfolio here. And so there, I would say the overlap with fusion certainly is in developing and understanding cable architectures. Both fusion and high energy physics would typically want to have some means of scaling the current to allow us, give us flexibility in the design for how much current we use versus the inductance of the magnet. That plays a role in defining our protection circuits, et cetera. And so we want to develop cable architectures, and fusion is doing that. We're doing it, and so we overlap. Of course, the biggest way that we're working with fusion is, of course, buying lots of conductor. And by buying lots of conductor, that is influencing the cost of REBCO. It's, of course, in the near term, is kind of hurting availability. It's pushing these companies at the limit of production. So sometimes it takes us longer to get conductors. But it's definitely already showing a significant impact on the cost of REBCO. And of course, with the fusion, we also are working with many of these companies, Brookhaven, Berkeley, I'm pretty sure Fermilab as well, and Florida, all of us, people have collaborations that kind of are very synergistic with MDP, where we are working with the fusion companies to help develop certain technologies, whether it's certain diagnostics, whether it's certain models, whether it's testing certain cables, et cetera. So there's a lot of very close connection between MDP's R&D and what industry wants from labs and universities. So it's a lot of connections.
Akira Yamamoto has written into the chat, how does MDP collaborate with Fusion HTS magnet community to maximize synergy more in the future?
Yeah. So I think so certainly when in the US, at least, we have these public-private partnerships, and we try to leverage those, so that those are typically funded by Fusion Energy Sciences. In some cases, of course, companies come directly to the labs or the universities through sponsored projects. What is a bit missing in the U.S., at least, is a strong national program in fusion magnet research. There is some investment, and so at Berkeley, and I think at Florida, there's some competed proposals that were funded to support magnet R&D for fusion. And so kudos to FES to do that. And of course, when we do those kind of proposals, we make them very synergistic with MDP. so that we're focusing on the fusion needs, but we're leveraging MDP and vice versa. Anything that we develop within that fusion proposal that is relevant to MDP, of course, that synergy happens. Where I think there's a bit more work to do is getting industry to be very open with their results. They've been pretty good, but I think there's always a danger that in industry, there might be a tendency to tout the positive and to not tout the negative for their own funding benefit. And so that's always a bit of a concern, right? In the public sector, we basically try to publish everything we have, the good, the bad, and the ugly, so that we're all learning together. And so that's a challenge for us to work with the fusion community when so much of it is driven by the private sector right now. But overall, I would say the relations are good. Industry, for the most part, is fairly open. And we see that through workshops, et cetera, with a lot of presentations from many of these startup companies. So.
We have a question from Marcel Demarteau. Can you comment on the use of iron-based superconductors for magnets for HEP?
Yeah, that's still a big uncertainty there. So that's really being pushed by China. I think Japan had some early inroads in that, but I think China is really pushing that heavily. And there is strong potential there. It's not totally clear if that potential can be materialized. So for large scale, and so that's really the question. I don't think we have seen enough data to convince us that it has passed the bar where it's highly relevant for high field applications. But we just need to either get hands on some of the conductor that's being used there, or a better insight into the real performance of these iron-based conductors. Certainly, what's appealing is the potential for very low cost and high field, and properties that are relevant to high field and accelerated application. So that's why China is doing it. Is that potential for low cost? But I think what we haven't seen is sufficient current density in real wires or tapes that we could get our hands on. And so I think the jury is still out on those iron-based superconductors. We're all ready to jump on them if they're real.
We got a follow-up question from Akira Yamamoto, which says, in your personal view, on what timescale shall we expect realizing accelerator HTS magnets?
It's a good question. I do think things are evolving fairly quickly. So, I mean, I showed the 6 Tesla result here. CERN just is presenting 5.6 Tesla or something recently. They're working on designs to 10 Tesla. So far, I don't see anything. We certainly think that the magnet that I showed, the 6 Tesla, there's no reason in our minds that same essential geometry could comfortably get to 10 Tesla. So I think we see a fairly rapid development process going on. There are some big challenges down the road related to protection of these kind of magnets. So the higher the field you go, the longer the magnets you go, the larger the stored energy. And protecting HTS magnets is really probably one of the biggest challenges. And frankly, if you talk to folks who've been around a long time, especially in the fusion community, they will point out that, hey, wait, there's not been any magnet with very large stored energy made of HTS that has survived. Now, some people might argue that's in the fusion community, they may say, wait a minute, we've done certain things. But the test results we've seen, for example, they've gotten to a high field, and then later they damage the magnet, perhaps on purpose, but still the magnet was damaged due to a quench. So it hasn't been reliably shown to be that we can protect them for large scale application. Doesn't mean we can't, but we haven't been able to prove it. And part of the challenge there is these are very costly magnets to build, so it's not an easy thing to test, destroy like we do in a traditional development process. So one of the big opportunities there in HTS is to develop a paradigm where we don't ever quench the magnet. HTS magnets don't train, or we don't think they train in general. And so if we can design them so that we can see an impending quench, that might occur in the future and back off, and just never quench the magnet. That's one paradigm that we're exploring. It might not work. There might be too many extraneous energy sources that might cause spontaneous quenches. But so far, that looks like an appealing possibility. But so that's one of the big challenges for going to large scale, high field, long lengths HTS magnets for accelerators.
Are there any more questions for Soren? I don't see any. So we now have a break of 29 minutes. So the next talk will start at 3:40 Eastern Time.